My name is Odong Jasper. I'm a second-year student of Wisdom University pursuing a Bachelor of Science in Water Resource Engineering. Today, I'm so privileged. I want to take this golden chance to introduce to you my newly created YouTube channel by the name Ripple's Channel. Ripple's Channel. And it is Ripple's Lectures Channel. So please master the name. It is Ripple's Lectures. Please, I want to encourage all of us, both our friends locally and internationally. Please like my videos. Please subscribe to my videos. Please comment my videos. I want to say that together we can make it. Nothing is beyond limits. Nothing can limit a mind. A powerful mind can do anything. So I want us to go together step by step. I have a passion to lecture, and that's why I've opened this YouTube channel. So when it comes to lecturing, I assure you to be interesting. It will be comprehensive, it will be interesting, it will be well researched. Be blessed. Today I want us to take on the first video on hydraulics. It will be on hydraulics. It will be on hydraulics. Hydraulics is a course which is studied in engineering, and under hydraulics, there are very many things. They're going to cover open channels, they're going to cover pipe flow, they're going to cover very many things, even pumps, turbines. That's under hydraulic machineries. That's what we're going to begin with. We're going to begin from hydraulic machineries together. Hydraulic what? Machineries. Hydraulic machines. So on hydraulic machines, there are very many machines we're going to cover. We are going to cover a pump, we are going to cover a turbine, we are going to cover Pelton wheel, we are going to cover centrifugal pumps, and so much more. So but today, we are going to begin our first YouTube video with pumps and turbines. We are going to begin our first YouTube video with pumps and what? And turbines. I'll be so much slow, so that all of us can get the best, can get the content. You can even master the blackboard. Because for me, I believe that when I teach with all my heart. So I want us to be so serious. So today we're going to, under subsection A, we're going to talk about pumps. There is pumps and turbines, but we're going to talk about pumps first, then we go to turbines after. So under pumps, you're going to cover only one concept for the first video. I hope you will like it. Under pumps, you're going to cover the concept of power. Together, what? Power. So what is power? I want to define power in the simplest way. So power is the rate of doing work. Power is the rate of doing what? Work. You get? So under power, we're going to talk about power output, and then what? Power input. So under power, since we're going to talk about power output and power input, that means you introduce another concept called efficiency. Another concept called what? Efficiency. And this is now the first formula you should master under hydraulic machines. The first formula, what it means cramming it, what it means what, please understand it. But I'm not going to make cram it, I'm going to derive it for you, my friends. So efficiency, we are going to begin by pumps, since pumps is the first, maybe turbines after sometimes. So under efficiency, we are going to talk about efficiency, and efficiency, by definition, efficiency is given by this symbol. And efficiency is given by power output divided by power input times 100%. You get? Efficiency is given by this symbol, which is given by power output over power input. So now for a turbine, you are going to derive an expression for the power input. I'm going to derive it for you because I don't want to cram. You know, when you understand where it comes, you can easily understand it. So let's call this one maybe equation 1. So under power output, let's derive the formula. let's say but, please, I want to follow me very well, but power is equal to the work done, since I define power as the rate of doing work. So power is work done divided by the time taken. So, but what is work done? Work done is given by the product of force and the perpendicular distance. I hope you are following very well. So over time, let's call time as small t. And then we also know that force is given by the product of mass and gravity. That is the force. Then times the distance divided by t. Follow me very well, please. Then, but again, we know that the mass of any substance is the quantity of matter in a given body. So mass is the same as density times volume. Density times what? The volume of a substance. Let me substitute here and we'll come up with an expression. It will be density times volume times the action due to gravity, then times that distance there. That distance d. Yeah, d over t. But again, you will agree with me that the ratio of volume to time is discharge, because discharge is given by the unit meters cube per second. So which this meters cube is volume, then this t is time in second. So we can now say that this thing here, volume over time, is what? Discharge, which is q. So we can substitute. So power will be equals to rho q times g times. Now for pumps and turbines, we also deal with heads. Head, the pump head. So which this d, we can change it as h, which represents the head of the pump. Let me say where h is the head of the pump. Please follow me very well. So this is an expression for the power output of the pump. So as we continue, we can now take this formula and substitute it back inside here. So let's continue. We can go to this part of the blackboard. So I can easily conclude that the efficiency of a pump, which is this symbol of a pump, is given by, so I will substitute this formula here, which is rho, which is the density of the water, and then the q, which is the discharge, then the g, action due to gravity, then the h, which is the head of the pump. I pick all this formula and place it inside here in the pump output. So that means, in summary, let me just say, the power output of the pump is density times the discharge times g times h. You get? So there's no need of cramming, because I will drive for you every formula step by step and you understand it. So this is the power output. I can take this formula and substitute it back here. So efficiency of the pump is going to be equals to power output, which is going to be density times the discharge q times the action to gravity g times the head of the pump divided by the power input. We get? So this is the master key. Let's give it a box, something like a house, because this formula you should master it. When it comes to calculation purposes, you should know that the efficiency of the pump is density of this, which represents the water, because the pump lifts water. Then you talk about the q, which is the discharge, the g, which is the action to gravity, is 9.81. We know that our g is 9.81 meters. 9.81 meters per second squared. So that is the action to gravity. We are going to substitute here. Then the head, so it shall depend on the question. But just master the efficient pump is given by this. If you cannot master all this, you can derive it step by step. Now, let's now look at an example. Let's now look at an example of how to use the efficiency of the pump. Please follow me very well, because I want you to understand the basic concept of pumps. Then as we go to turbines next time. So let's read the question. The question is saying a pump lifts water from a large tank at a rate of 30 liters per second. So 30 liters per second, it is is discharge. So that means we are like given a discharge. You can summarize the question simply. You can say given, we are given discharge, discharge which is Q, and it is 30 from the question liters per second. Please follow me very well. The things are simple, but since I have the passion to lecture, I want to make you understand it, and then you will like it. It will be interesting, comprehensive, and well researched. So, but the unit of discharge, it is meters cube per second. So we can change it on meters cube per second. So we can say it's going to be equals to 30 times 10 power negative 3 meters cube per second. So what is this? When you divide this, what do you get? When you say 30 divided by 1000, you get 0.03 meters cube per second. This is what our discharge. You get. But this is just a small conversion. But if you want to go by from past principle, there's no problem. You can go through it. You can say 1 liter is same as 1000 cubic centimeters. Then you say 30 liters is same as 30 times 1000. You see that? So it will be wasting time. So then you say 30,000 centimeters cubed. Then again, you have to change centimeters cubed to meters cubed, which will be a waste of time. You know, to change from centimeters cubed to meters cubed, you must divide. Because this is we are changing from small to bigger unit, so you divide by 1 million. It will be equals to 30,000. I think 30,000, yes, over a million. Because 1 meters cube is around 1 million centimeters cube. So you cancel this and this. You cancel this and that. So you find that it comes back to that. It is around 0.03 because it is 0.03. So that is it. If I want to go long, we can go through this. But if I want to be an expert, go direct because time is money. Next, let's summarize the question. If the input power is this, so that means the power input is given power input. You can summarize the question. Power in is going to be equals to it is 10 kilowatt, and kilo is 10 to power 3. So you convert the units, it's going to be 10 to power 3 watts. We get. Then we have also the efficiency. So the efficiency of the pump is going to be equals to 40%, which is around I think it's going to be 40 over 100. You cancel this, so we shall have 0.4. That's the efficiency of the pump. So what are they asking? They're asking for the head developed. So the head is that H, which was D, I changed to H because the pump pumps water and it develops a head after. So it will be, so you can pick from the formula for the efficiency of the pump. So since I've derived it, I'm just going to quote it. So let me say using efficiency of the pump is going to be equals to the power output divided by the power input times 100%. So the efficiency of the pump, we have 0.4, not waste time. It's going to be equals to the power output. We derived the formula last time, a long time ago, so it will be rho Q times G times H over the power in. You get? So it will be 0.4, the same as density, because the pump leaves water. We're talking about water. So since water, the density will be density of water, which is 1000. So times the discharge is 0.03 times the G. The G is action to gravity. I told you it is 9.81 times the head. The head is not given, so it's going to be H. That's what I asked in the question. Divided by the power in. Power in is given by 10 times 10 to the power 3. So when you compute all this, somebody compute. So when you compute this answer, you can compute to get the head. You can just press 0.4 10 times 10 power 3, divided by 1000. Yes, the answer is going to be, if compute very well from the calculator, it's going to be 13.6 if round off meters. So the head is in meters. So this is the answer. So I want to thank you very much for today. So next time we shall be talking about how to get the maximum height. The maximum height. I want us to go step by step. I don't want to do very many numbers at the same time. I'll first do the head. Next time I'll do the maximum height, which the pump can pump what the maximum height, the elevation. So I want to thank you very much for listening to me. I want to remind you that it is Ripple's Lectures, my YouTube channel, and please, I want to encourage you to subscribe. Please like my videos. Please share and comment. Thank you very much, my viewers. Meet next time.